Next up, let's look at improving our RAG system even further with contextual embeddings. So if we look at the chunks that we have saved in our vector database, I think this is a good example of a chunk which kind of lacks context. It's starting what appears to be in the middle of a sentence. It's got an array of random enough numbers. There's a couple of terms thrown in, but it really isn't that obvious what this chunk is about. And this is the real limitation of RAG systems. The chunks are created independently of each other. So if the previous chunk to this was actually setting the scene or defining some of these terms or these features, that chunk might not be retrieved, and then the agent wouldn't have visibility of it. So that's definitely going to hurt the actual accuracy of what the RAG agent is generating. So by contextualizing the chunks, what we're doing is we're adding in a section at the top of each chunk to set the scene for the chunk. So this was popularized by Anthropic in their contextual retrieval paper from September last year. I've created an entire video on this on our channel, and this workflow that you see here is available in our community, which is contextual retrieval with context caching. And here we're using Gemini to actually generate these chunks or these snippets that are added to the start of each segment. I've also created a workflow and a video on cache augmented generation or prompt caching, because these two concepts go hand in hand. You're going to the LLM for every single chunk, and you're providing the entire document every single time. And that way it can situate the chunk within the document. The problem with that is it's really expensive and it's slow. And LLM providers know that, which is why they've brought out prompt caching. And prompt caching is a lot cheaper, which makes contextual retrieval more affordable for users. So when looking at our RAG ingestion pipeline, the area that we're going to need to change is down here, where we're setting up the text for embedding and sending it into the Supabase vector store. And similar to re-ranking and hybrid search, N8N doesn't have any contextual retrieval nodes we can use, so we need to build up the constituent parts. And for this, we'll use OpenAI's prompt caching. Of the three main providers, OpenAI's prompt caching is the easiest to actually use. The problem with it is there's only a 50% saving on tokens in cache, whereas with Gemini it's 75%, and with Anthropic it's upwards of 90%. So let's make some space. We have our text for embedding here, which is essentially what we're getting from this node. So what we need to do is we need to chunk this manually. Because if you click on plus, and if you go to AI, and then other AI nodes, you'll see that there are text splitters. But these text splitters only work as subnodes of a main vector store, as you can see there. So they actually have to be joined like that. So that's not going to work for this use case. So if we create a code node, again, I've got AI to generate a chunking script for me, which you can see here. So this is a recursive character text splitter. It's chunking based on a size of 1,000 characters with an overlap at the start of 200. And then we've set separators and boundaries. So this should now take our text and provide the chunks the same as what's actually happening here. So let's rename this chunking, and let's drop a file into the folder here so we can test our chunker. Now that's uploaded, and let's click test workflow. And then what we'll do is let's actually just pin all of this data, or pin as much of it as possible. If we test that again now, it should flow through it all, which it does, and we are hitting this node. Excellent. Oh yeah, we have the wrong reference to the text here. So that is content. And if we test it again, yes, so that has worked, and we're getting 611 items. So actually, that's quite a large document to be testing with. Let's get a different document up and running. Yeah, this one is 16 pages. That'll be better. Now I'll just need to unpin and repin everything. Yeah, that's better. 58 chunks. So that's a bit more manageable. So let's move all of this along. And now with these chunks, we now need to loop through them to generate embeddings. So we're going to use a loop over items. And the other thing is we don't need to do this in batches of one chunk at a time. This very much depends on what rate limits you have with your LLM provider. I'll set this at 10 for the moment. So there's my loop. And let's name this loop over chunks. And now what we can do is we can go to OpenAI and we can use the message and model option. And we can choose a model to use here. Now we're going to be hammering this API. Every single time a chunk needs to be processed, we're going to be sending a trigger to this LLM. So I wouldn't use anything too expensive. So maybe 4.1 mini, maybe 4.1 nano. Let's try mini for the moment. And if we go to Anthropic's contextual retrieval document, they actually include the prompt to be used in this. And this is it here. So let's copy out this prompt and we'll drag it in here. And let's just set it as an expression because we are going to be loading dynamic variables. And we have undefined. And where it says whole document, you can delete that and just drag in the content of the entire document. That's that there. And then for the chunk, you can drag in the text from the loop. Now we actually need to execute previous nodes to see that. So we'll just delete that for a second. Okay, so let's run this now, just so that we can load up the data into memory. And we can stop it straight away. Now, so we have our chunk at the loop, so we can drag it in there. And if we zoom in, let's have a look at what we're saying here. So first of all, we're passing the entire document. And then we're saying, here is the chunk we want to situate within the whole document. And we pass the chunk. And then we're saying, please give a short, succinct context to situate this chunk within the document for the purposes of improving search retrieval of the chunk. Okay, and let me just check the rate limits. So 4.1 mini has a 10 million tokens per minute limit, which we could hit. So that's something to look at. We're not going to probably send 10,000 requests per minute, but definitely the token limit we may hit. So that's something that we'll just need to be conscious of. I suppose it depends how fast this returns as well. And maybe for the moment, let's even just set the loop size to 1, just to get this up and running with a single chunk. And then we can increase the batches and increase the scale. So we'll test it out again, and it's finished. We haven't looped it back, so it's just ended there. And if we double click, now you can see this chunk contains the title page, publication, table of contents for the 2026 Formula 1 Power Unit Sporting Regulations. Excellent. So let's rename this one Generate Chunk Description. And now what we can do is just line up the text that can then go to the vector store. So we do edit fields, and that's essentially what we've done here with setup text for embedding. But this is actually setup chunk for embedding. So we'll call it content. And here what we're doing is, if we set the value as an expression, we're firstly going to provide the chunk description, and then we can provide the chunk. And then that's what's going to be embedded for this chunk, and it's grounding and situating the chunk within the context of the document. So then that can go to Superbase's vector store. For a default data loader, we could just set a really high chunk size. This will be 1,000. There's only a single chunk, but this is a required node. You can't just delete it. So we'll just set this to 100,000. Okay. We're going to use the same embedding model. That's fine. And then after that chunk has been embedded and upserted to the vector store, we can then go and process the next chunk. So we'll drag it back to the loop there. And then this replace me branch, let's get rid of that. And then when all of the chunks have their descriptions created and have been upserted to the vector store, we can then drag this down here to continue to the next file. Okay, so I think we are ready to test this out. So let's just make sure the actual loop works correctly. That looks good, yeah. It's just incrementing one by one. We can stop that. And actually, out of interest, what's the size of the tokens that we're sending here? Do we have any logs or any information on that? I'll need to dive deeper into the monitoring to actually figure that out. Because when I built this out before, we needed to actually build out a wait function to get around some of these rate limits. Anyway, let's scale this up now and let's go to batch size, let's say 10. So now it's hitting that 4.1 mini API 10 times per loop. So you can see why you can get rate limited with this approach, particularly because we're hitting an LLM. It's not an embedding model like it is here. But that was fine there. And an approach here actually is to just set retry on fail and actually provide a high enough wait. So the max is 5 seconds and the maximum of times you can try is 5. So we'll set it as that. Now we have 58 chunks in this document. So we're halfway through already. Contextual retrieval and the generation of these blurbs or these descriptions really slows down the actual ingestion process, as you can see here. Now, if we were using GPT 4.1 Nano, it might be faster and we might end up with the same results or the same quality. So you could play around with that and test it and see what works and what doesn't work. Okay, so it's finished processing that document. So if we just go into this now, and if you scroll down to the usage, you can see the prompt token details. So this inference to 4.1 mini took 10,000 tokens, of which the vast majority of them were cached. But this is where the 10 million token limit per minute kicks in, because with that size document, if you triggered that 1,000 times, let's say in a minute, you would hit the max, which you might struggle with in this flow. But if that document was 10 times bigger, you would only need to trigger it 100 times to actually hit the limit, which is definitely possible in this loop. So that is something that would need to be designed around maybe some sort of counter of tokens. And once you hit that 10 million tokens within a certain time frame, you pause for a period of time. And that way you'll be able to make it a lot more resilient. And now if we jump into our vector database, and if you have a look now at the chunks, it's really interesting. So every single chunk has this blurb at the start. This chunk is from Article 4.2.2 of Appendix 1 in the Power Unit Regulations. And it talks about the specific area of that subsection and what it's all about. So this is incredible grounding of the chunks. And it just means that you're not really losing much context now by chunking. And based on the benchmarking that Anthropic carried out, by using this approach, along with using re-ranking, which is what we're doing here, and with using hybrid search, which is what we're doing here, it reduced the error rate or the failed retrievals down to 1.9% compared to standard embeddings, which had an error rate closer to 6%. So I'm now running the full file import end to end. I've increased the batch size to 50 just to see how it handles it. Yeah, that seemed to perform okay. These are obviously pretty hardened APIs with OpenAI. I do find Anthropic's APIs can be a little bit hit and miss. They tend to go overloaded quite a lot. Okay, it's archiving the file. There's only one file to import. And if we come into our vector store, we have our 58 chunks. We have our document with its hash. And it has archived the file. And that file is upserted. Brilliant.